So here's a nice set of instructions from your textbook, how to predict molecular geometries. First step, draw the Lewis structure. If you can't draw the Lewis structure, you're going to have a real hard time with VSEPR theory. From the Lewis structure, figure out the total number of electron groups. Figure out how many of those are bonding groups and how many are lone pair groups. Statement 4, I think, is stupid. Refer to table 10.1. Well, what if you're taking an exam and I don't give that to you, and I'm not going to? So that's not a good idea. Think about how balloons would arrange themselves. Think about how many total groups do I have? What shape did the balloons make? Right? Linear, trigonal planar, tetrahedral, trigonal bipyramid, and octahedron. It's not that many. And then, if you have lone pairs, imagine that the lone pairs are invisible balloons. Your molecular geometry is a description of what's left. These will probably show up as multiple choice questions, and so you don't necessarily need to remember exactly trigonal bipyramid, but you need to be able to recognize that as one of the choices. Let's predict the molecular geometry and bond angle for ClNO. It's kind of an odd molecule. I'm going to put nitrogen in the middle because that's what's suggested by the formula. We have to figure out the number of valence electrons that we're going to have in our Lewis structure. Chlorine has 7 valence electrons. Nitrogen has 5 valence electrons. Oxygen has 6 valence electrons, and I believe that adds up to 18. So we already put in 2, 4, 6, 8, 10, 12, 14, 16, 18. You start handing out electrons. I couldn't give everyone an octet. That means I need to make a multiple bond. Just as sort of a reinforcement of drawing Lewis structures. Where do you think would be best to put that double bond? Between nitrogen and chlorine or nitrogen and oxygen? Nitrogen and oxygen. The reason there is that oxygen prefers to form 2 bonds. When oxygen has an octet and forms 2 bonds, its formal charge is 0. Chlorine likes to form 1 bond. Chlorine already has 1 bond. If we put another one in here, it's probably not going to be very happy. We're always going to try to shoot for 0 formal charges. Nitrogen likes 3 bonds, and so no matter where we put the double bond, it's going to be fine. So I'm going to choose to put the double bond between nitrogen and oxygen, which means that I'm going to have to move one of my lone pairs, right? Because right now, I've got too many electrons. So I took one of those lone pairs and moved it. Now I have the correct number of electrons, but the nitrogen has too many. So I'm going to take this one and give it to the chlorine because the chlorine didn't have enough. 2, 4, 6, 8, 10, 12, 14, 16, 18. Everyone has an octet and a 0 formal charge. This is a winner. That was step 1. Now what do we do? How many electron groups on the central atom? 3. There's a single bond, a double bond, and a lone pair. 3 groups. So, how do 3 balloons get away from each other? They form a triangle, right? So 3 groups making a triangle like that. That would be the electron geometry, trigonal planar. But we're asking about the molecular geometry. Do we have any lone pairs on that central atom? Yeah. So we need to make one of these a lone pair. So the lone pair is in this position. You could draw it like that if you want. It's there, it's repulsive, and it's affecting these two. Now one of those is a double bond, so maybe we should, be sort of accurate and illustrate that. So that's the lone pair. What would we describe the atom shapes, the molecule shapes? It's bent. So the molecular structure is bent. And it's asking us to predict the bond angle. Well, there's only one bond angle. It's the angle between those two bonds, because this is a lone pair. If this was a perfect trigonal planar structure, what would that angle be? Not 180. 120. So this would be 120 if they were spaced out equally, but this is more repulsive, causing these guys to get a little closer together, so it's less than 120. I'm not asking you to predict any specific angle, just less than 120. Any questions? We're running over time. Let's do this one. I3 minus. What's the first thing we have to do? Lewis structure. So Lewis structure, we got 3 atoms. We don't really have any choice but to just stick them in a line. Then we need valence electrons. We have 3 iodine atoms. They each have how many valence electrons? 7. And what do we do with that -1 charge? We add an electron. So I believe that's what, 22 valence electrons? So we've got 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. Oh, this is weird. I got octets, but I still have another pair of electrons. You can check your math, but it's right. Can iodine expand its octet? Yeah, I can. Because iodine is in the 5th period. Elements in the 3rd period, 4th period, 5th period have d orbitals available. And so we could put a couple extra electrons in those d orbitals. So that extra electron pair that I'm looking for a place for, I'm going to stick on the central atom. Brackets and a negative charge because it's an ion. So there's our Lewis structure. Now what are we going to count? Electron groups on the central atom. How many are there? 5. 2 bonds, 3 lone pairs, makes 5. So what do 5 balloons do? It's that pink and red one right there. Yeah, that's gonna look better. So 5 does this, right? A trigonal bipyramid. We got 1 on the top, 1 on the bottom, and 3 around the middle. So that's our electron geometry. Do we have lone pairs? Why, yes, we do. We have 3 lone pairs. In a trigonal bipyramid, where do the lone pairs go? They go along the middle, the equator, right? Because they have more space. These angles here are 120, and these angles are 90. And so they've got more space around the middle. So we're going to put the lone pairs around the middle. So there's a lone pair kind of back there, and one sticking out in the front, and then one over there. The molecular geometry, we're just looking at where the atoms are. So what's the name of that? Linear. Any questions? This is your book's attempt to show you how we would represent three-dimensional things on a two-dimensional surface. So like if we were doing methane, you want to draw as much of it in the plane of whatever it is you're doing as possible. So I'd put these guys all in the same plane. They're just using regular lines. And then one of those is going to stick out at us, and the other's going to be behind. And so the one that sticks out is a solid wedge. It's coming out at you. And then the one that's behind is a hatched wedge or a dotted line, because it's behind the screen. So this hydrogen is sticking out, and that one is actually behind the screen. So it's three-dimensional. When we have larger molecules, we have more than one interior atom. And what we do is we look at the geometry around each interior atom. So here's our Lewis structure, and we can look here. This nitrogen has 4 electron groups. That's tetrahedral electron geometry, but 1 lone pair, so that's a trigonal pyramid. Here we have 4 bonds. 4 electron groups is tetrahedral. No lone pairs, it stays tetrahedral. This carbon has 3 groups, trigonal planar. The oxygen has 4 groups, tetrahedral, but 2 lone pairs, so it's bent. So let's do an example. So I'm going to take this and just expand it into a Lewis structure. So there were 3 hydrogens on that carbon, and there's, a hydrogen on this carbon. And then to account for all the electrons, there's lone pairs on that one and this one. So looking at this carbon, how many electron groups? 4. Yep. Are there any lone pairs? No. So the electron geometry and the molecular geometry are the same. That one's tetrahedral. How about this carbon? How many groups? 3. 3 groups is a flat triangle, right? Trigonal planar. Are there any lone pairs there? Nope. So that's trigonal planar. And then we've got this oxygen over here. How many electron groups? 4 groups. 2 of them are lone pairs. So that's a tetrahedron with 2 of the balloons being invisible. What's the name of that? Bent. Because a tetrahedron, you're not going to have anything in a straight line. And make a sketch of the molecule. When you need to do something like that, again, you want to make everything be in the plane of the screen that you can. Make it as flat as possible. I'm going to start with the carbon in the middle and make that double bond to the oxygen. And then it's going to have approximately 120-degree angles to the carbon and the oxygen. Then this oxygen is going to be tetrahedral with the hydrogen. So that's hydrogen, this is oxygen, that's carbon. This is oxygen, and this is carbon. And then this carbon is tetrahedral with those hydrogens. So we could put one in the plane, and then we've got one kind of sticking out at us, and one kind of going back behind. Good news is, I won't make you do that on an exam. Largely because I don't want to have to look at it, because they can get pretty ugly, as you can imagine.